I am Evangelos Albanis, and I will talk about axion-mediated photonic transitions in high-quality factor dielectric resonators. Let's begin by defining the charge parity symmetry. The charge conjugation flips the charge while the parity flips the handedness, as shown here and here. The combination of the two, named CP symmetry, claims that the laws of physics should be the same if a particle is interchanged with its antiparticle, while the spatial coordinates are inverted. However, in 1964, Cronin and Fitch showed experimentally the violation of the CP symmetry under the weak force K on dk. They received the Nobel Prize in 1980 for their discovery. So, the CP symmetry is violated in weak force interactions. Now, what is the strong CP problem? Quantum chromodynamics, or QCD in short, allows a term that violates CP symmetry in strong force interactions. However, no experimental evidence of this has ever been found. This is puzzling because there is no apparent reason in the theory for this parameter to be so close to zero. One explanation would be fine-tuning, but fine-tuning is not a satisfactory explanation in physics. In this frame, during the 70s, Roberto Peccei and Helen Quinn proposed a new symmetry that results in a term that dynamically minimizes the CP violating term. This symmetry requires the introduction of a new field, the so-called Peccei-Quinn field. The Peccei-Quinn field introduces a new light pseudoscalar boson. Later, Wilczek and Weinberg named the particle Axion. This name came from a very popular laundry detergent because its existence could also clean up the dark matter problem. So, if axions exist, they address both the strong CP problem and the dark matter constitution. As you probably know, axions have not been detected yet. There are two problems with this. First, their mass is unknown, and second, their coupling with the electromagnetic field G A gamma gamma, as you see here, is extremely weak. This slide summarizes the ongoing efforts to detect the axion. This is the parameter space, the coupling constant versus the axion mass. It covers a broad parametric region, but we tend to believe that the QCD axion lies in the micro EV to the MeV range. And with yellow color here are the theoretical QCD bands for expecting the axion. However, there could also exist other so-called axion-like particles with different masses, and therefore people is scanning over a broader range and even broader than this one. The detection strategies vary from haloscopes to helioscopes and light shining through walls experiments. And there are many future directions like these mentioned here and many others. Let's break down the axion-photon interaction. A photon at an initial state I absorbs an axion and produces a new photon at the final state F. The opposite process is also possible. A photon at an initial state I emits both a photon at the final state F and an axion. Therefore, axions can act as an energy reservoir for photonic transitions. Such processes that involve two photons and one axion are extremely rare, and the idea is to find a way to enhance both the initial and final photon intensities. It is known that dielectric resonators of high index exhibit the so-called optical mi-modes. They are states almost confined inside the resonator with high lifetime. In the x-axis of this plot, we have the frequency of the photon, and in the y-axis, we have the scattering cross-section spectrum, and you can see the mi-modes as sharp peaks in the scattering cross-section spectrum. And as you can see from the field profiles, the photon field is actually confined mainly inside the resonator. And each resonance for a spherical scatterer is characterized by the polarization transverse electric or transverse magnetic and the angular momentum index L. The increased lifetime and intensity increases the possibility of interacting with matter. Typically, this strategy is followed to increase the interaction between the photons and matter excitations such as magnons or phonons. But what if axionic excitations exist in the background? Could this strategy work also? Our strategy works as follows. We first write down the almost discrete states of the mi-resonances, as shown schematically here. For a spherical particle, those modes can be written down analytically, as you can see here, the TE transverse electric modes and the transverse magnetic modes, the electric field and the magnetic field, where c is the velocity of light in vacuum, while q is the wave number. JL are the spherical Bessel functions, and x bold are the vector spherical harmonics. And the question is, can we have axion-mediated photonic transitions between different states? The interaction between axion and photon is described by an additional term in the Maxwell Lagrangian, where A is the axion field, Ga gamma gamma is the coupling constant, and A and B are the electric and the magnetic field, respectively. Now, in the presence of this term, the Maxwell equations can be recast as follows, where you see new terms here and here that are proportional to this coupling constant G, A gamma gamma. If we set the following constitutive relations for the field D and the field H, the Maxwell equations that we obtain are the following, where, as we can see, these equations are identical to the common Maxwell equations in matter, but this time it is analogous as light is traveling in an axionic medium that mixes the electric and the magnetic fields. Now we will model the axion as a time-dependent perturbation. In the case of cold dark matter, the axion can be considered as a coherent classical field, where the frequency of the oscillation, omega capital, is related to its mass through this relation, while in this treatment we approximate the galactic axion field as monochromatic, since its expected quality factor is very large, namely almost 10 to the 6. Now, we recall that in an optics experiment, there is the so-called Brillouin scattering, where light is inelastically scattered by a time-dependent oscillation of the material. For example, we shine a laser at this frequency, and in the presence of a matter excitation, two sidebands appear, one for absorption of one quantum of the excitation and one for emission or a quantum of an excitation. The idea here is to adjust the central peak to a Mi resonance and the one sideband to another Mi resonance. Using this strategy, we can obtain resonant transitions. We can model the interaction as follows. The constitutive relations can be cast as a linear system in matrix form as shown here. This matrix consists of two parts. One part which is a static one and one part which is time dependent. This is the dynamic part. Following this, we can write the classical Hamiltonian density, the energy, in this form, where, as we can see here, it can be split in two parts, where the one part, H0, as you can see here, is the unperturbed Hamiltonian, which is a typical Hamiltonian density for an electromagnetic wave traveling in a linear medium having relative permittivity epsilon and relative permeability mu, while this term, delta H, that contains all the axionic information, can be considered as a small time-dependent perturbation. The axion-mediated photonic transitions that we will discuss later on arise from this dynamical perturbation of the system. Since the axion-photon coupling is very weak, we can apply the Born approximation up to the first order to calculate the transition amplitudes. In view of this, the useful information is provided by this overlap integral or transition matrix element, where the perturbation delta V is sandwiched between the final and the initial optical states. This is the final state of the electromagnetic field. This is the initial state of the electromagnetic field. And this is the perturbation delta V from this matrix. The overlap integral takes this form where the delta functions express energy conservation in the optical transitions that involve absorption and emission of one axion by a photon, and this G here has this form. Now we must find the selection rule that governs such transitions. We write here the symmetry group of the sphere, which is the O3 group that involves both proper and improper rotations, and this is the character table. The question is, which is the symmetry of the perturbation? Since the amplitude of the action A capital is pseudoscalar, it is straightforward to show that delta V, the perturbation, remains invariant under proper rotations r theta, while change is signed under inversions I and improper rotations I r theta. Therefore, delta V is an irreducible tensor operator which has the symmetry of the du L equals to 0, where U denotes the ungerade parity, the odd parity, while G here denotes the gerade or even parity. This gives us the following selection rule. This is the symmetry of the perturbation, and if this is the symmetry of the initial photon state, gerade, even, with a particular L, then the final state should have the opposite parity, ungerade, but the same L. And if the symmetry of the initial state is this, is ungerade or even, with a particular L, then the final state should be of the opposite parity, gerade here, and the same L. This is schematically shown here that, for example, in the axion absorption, if the initial state has the transverse electric polarization and angular momentum index L, then the final state should have the opposite polarization, transverse magnetic, but the same L. And this is valid also for the emission of an axion. This is the initial state. If it has this polarization and this angular momentum index, then the final state should have the opposite polarization but the same L, provided that the frequency of the axion is the frequency difference between the two states. The complete theoretical formulation can be found in this archive paper. Now we assume a homogeneous dielectric sphere of radius s and relative permittivity 12, which is typical for silicon. In this graph, we show the corresponding resonance frequencies for both T and Tm modes in scaled units of frequency versus the L index ranging from 6 to 10. Such values of L are typical for high quality factor μ modes. We see an almost linear increase in the μ mode frequencies with increasing L. In this graph, we show the scaled frequency difference of modes of the same L. We see that this value remains almost constant, about 0.05. This means that the axion frequency should match this frequency difference. For axion masses at the range of micro eV, the particle radius would be in the millimeter scale, while the electromagnetic radiation will be in the microwave range. From the experimental point of view, such spherical resonators exhibiting μ modes in the microwave can be fabricated and measured experimentally, while microwave coupling to and from the dielectric resonator can be achieved using a small loop or dipole antenna placed in the near field, enabling efficient excitation and extraction of the desired resonant modes. The output photons may be collected by a frequency and polarization selective antenna optimized for the corresponding mode. Here, we emphasize that the proposed platform is fully scalable and can be adjusted to the targeted action mass. In this table, we show the correspondence guidelines towards the selection of the resonator parameters for targeted action searches. Since the results we showed earlier are in scaled units, we can adjust the radius of the resonator to target specific action masses. Furthermore, by targeting a specific mass window, for example an octave, it is possible to scan a portion of this window while keeping the resonator size constant and varying the refractive index of the surrounding medium instead. For example, embedding the resonator in a mixed liquid medium, where each liquid has a different refractive index, typically from 1 to 1.4, and is transparent in the microwave range, adjusting the concentration of the liquids allows for a gradual change in the effective refractive index of the embedding medium, permitting continuous scanning over roughly half of the desired octave. Now, for a particular action mass equals to 1 micro EV, we will estimate the corresponding photon-to-photon transition rate. This action mass requires this sphere radius in the millimeter scale, and these are the values of the frequencies in gigahertz for the corresponding optical modes, the transverse electric one and the transverse magnetic one, both with L equal to 10. We write down the Fermi-Golden rule, where this is the axion-mediated photon-to-photon transition rate. This squared G here is the matrix element we discussed earlier, and this rho is the density of optical states at the final frequency, EF. However, the actual transition rate should be multiplied by the number of photons accumulated inside the cavity. With these considerations, a realistic detectable transition rate using modern single photon microwave detectors should be higher or equal to 200 Hz. That corresponds to a coupling constant higher or equal to 1.22 10 to the minus 12 GeV to the minus 1, which is a value relevant for axion-like particles and not QCD axions. To target QCD axions of this mass, we must enhance the corresponding transition rate, and this can be achieved using advanced strategies that push the boundaries of today's technological capabilities. For example, we can use high quality factor whispering gallery modes to boost the optical density of states, together with high field materials, materials that can sustain very high fields because the number of photons accumulated should be increased, and we need materials with high breakdown threshold, such as silicon carbide or fused silica or even diamond. However, there is a practical limit to this procedure, which is set by the Axion field quality factor, which is 10 to the 6. Another problem is that nonlinearities may occur at high fields that add noise. A material with high nonlinearity threshold is diamond, which can be used. All these improvements combined can reach to a sensitivity of the coupling constant Ga gamma gamma up to 10 to minus 15 GeV to minus 1, which is our theoretical limit, since practical implementation might be challenging. For example, it will be challenging to pump the maximum number of photons inside the cavity, and a second challenge would be the thermal management. However, future efforts could overcome these limitations. Such calculations can lead to a new experiment proposal named Dark Rose from Dark Matter Search via Resonant Optical Scattering Experiment. With the rose color here is the projected sensitivity of such experiment in the parameter space for Axion searches, where black and gray colors are existing exclusion regions through current experiments, while the light gray regions are future experiments. Such an experiment could probe an Axion-like parameter space complementary to standard haloscope and helioscope searches, while for these masses, the projected sensitivity of the dark rose experiment intersects with the theoretical QCD bands KSVZ and DFSZ. To conclude, we have proposed a novel mechanism for axion-mediated photon-to-photon transitions inside high-quality factor dielectric resonators. The framework proposed here is fully analytical. Selection rules are derived using group theory and first-order perturbation theory applied for predictions. Our proposal is frequency tunable. The Mi resonator geometry allows precise tuning to match the axion mass. It is scalable. The platform is scalable and adaptable to different axion mass ranges. It is experimentally relevant and opens new pathways for tabletop axion detection beyond traditional haloscope and helioscope limits. And there are potential extensions. This framework can be adapted to the concept of solid-state axions in axionic media, which consist of novel topological insulating materials or telegen electromagnetic metamaterials. And I want to thank you for your attention.